cases.
Hello friends, welcome to this laboratory work of the subject Mechatronics Engineering. We are going to discuss the details regarding the experiments we are supposed to do in our mechatronics laboratory. To begin with, I'll be starting with strain gauge setup. As we all know, strain gauges are used for measurement of strain, measurement of displacement, measurement of velocity, measurement of acceleration. It is also used for measurement of forces and measurement of pressure. So this is one of the important transducers from mechanical engineering application point of view. Now, in our laboratory work, friends, had you come for the offline practical work, would have done the mounting work, but I would like to show you how to mount the strain gauges. The strain gauges, as we all know, as you can see here, the strain gauge. This is one strain gauge of 10 millimeter length. Now, the brown color that you can see is the backing material. Actually, the strain gauge wire is a very thin wire which is having diameter in microns, few microns, and its length is 10 millimeter. Like that, I can have a variety of strain gauges available in the market, and as per my requirement, I'll be selecting the strain gauge for my particular application. Now, this is a 10 millimeter strain gauge. It is a copper wire strain gauge, and this copper wire strain gauge is mounted on this specimen. As you can see, this is a scale, and this work is done by our past students. Now, what is done is, this will be the surface on which the strain gauge is to be mounted. So this surface is first of all cleaned with carbon tetrachloride, and thereafter with the fine polished paper the surface is cleaned, and then by using cotton gauze, once again using the carbon tetrachloride, the surface is thoroughly cleaned, and by using woolen cloth, it is all the particles those are accumulated on the surface are removed, and thereafter wherever I want to mount the strain gauge, the cross mark is made, and on the strain gauge also there will be one cross mark. So the cross mark that I have made on this specimen material that is matched with the strain gauge cross mark, and thereafter on the strain gauge on the surface adhesive, a thin layer of adhesive is applied. We use a regular adhesive that is available in the market, and by using that adhesive, thin layer of adhesive, by using a rubber pad, the strain gauge is slowly pasted on the surface of the specimen, right? And then by applying gentle pressure, it is located at my desired location. And thereafter, whatever two terminals those are coming out of those strain gauges, those are kept away from the adhesive material, and thereafter this mounted area is covered up by using a sellotape, and then we use rubber backing material also to protect the strain gauge from absorption of moisture as such, and that protection is kept for maybe 4 to 6 hours, and thereafter the strain gauge is ready for usage. Now, to check whether the strain gauge is properly mounted or not, what is done is, before mounting, by using a multimeter, the original resistance of the strain gauge is measured by using a multimeter. Suppose, for example, the strain gauge has a resistance of 250 ohm, let us say, and if I have done proper mounting, that resistance should not change, right? That is first check. So what we do, original resistance before mounting was 250 ohms, and after mounting I am going to connect my ohm meter, or by using multimeter I am going to check the resistance of the mounted strain gauge. The resistance should not alter. So that is the first requirement. Thereafter, while mounting, let us say if there is some air gap left, or some air bubble is left out, what is the check for that? What I do is, I gently rub over that mounted strain gauge, keeping the terminals of the strain gauge connected to my multimeter. What should happen? even if I scrub the strain gauge, even if I apply the pressure of the strain gauge, the resistance should not alter. If the resistance is altering, that means the strain gauge is not properly mounted. So these two checks are needed for checking proper mounting of the strain gauge. And friends, as we all know, this strain gauge, the gauge factor of the strain gauge, if you refer back the notes, the gauge factor is given by change in resistance, or dr by r upon dl by l. And K, the gauge factor of the strain gauge, is equal to dr by r. What is dr? Change in resistance, and r is the original resistance divided by change in length divided by original length. So this ratio provides me the gauge factor. Now the manufacturer provides me the data of this commercially available strain gauge. For this strain gauge, the gauge factor is 2, right? So what is the meaning of that? If you refer back to the formula, K is equal to resistance change upon, let us say, length change. What does it mean? The value of K, gauge factor, provides me the sensitivity factor. What do you mean by that? Corresponding to unit change in length, or corresponding to unit change in strain, how much resistance change I am obtaining. So if I say the gauge factor is 2, what does it mean? The resistance change corresponding to unit change in length or unit change in strain is double. So higher the gauge factor, higher will be the sensitivity of the strain gauge. Or in simple words, if the gauge factor is higher, the amplifying factor of the strain gauge will be higher, right? So I should try to use a gauge factor with higher sensitivity or higher gauge factor. So this is how the strain gauges are mounted. Now in the practical exercise, what we do is we study the performance of a strain gauge transducer, right? Now this itself can be used as a strain gauge transducer. As you can see, this is the beam. You can say beam with rectangular cross section, though it is a thin plate, but still it has got some thickness. So it has got some width B and it has got some thickness T, right? So if I just fix it like this, this will become a cantilever beam, right? If I fix it like this, it will be a cantilever beam, right? So when I apply some load here, right? So this will be a bending load, and because of that, there will be some bending moment that will be experienced by this beam with rectangular cross section. Now, because of this bending moment, bending stresses will be induced, or ultimately, some shearing stresses will be developed within the material of this beam. Now, because of the stresses and depending on the modulus of velocity of this material, we know the relationship stress upon strain is Young's modulus, isn't it? So, if I know the Young's modulus of the material and if I know how much stress I am developing, who can tell me how much will be the stress developed? As we all know, bending moment upon section modulus of this beam. What is section modulus? It is Z. So that section modulus is the ratio of I by Y, isn't it? So for this rectangular cross section beam, Z will be equal to, section modulus Z will be equal to 1 by 6 B into T square. 1 by 6 B into T square. What is T? T is the thickness and B is the width of this beam. So this 1 by 6 BT square, how I obtained? It is I by Y. I for this rectangular section is 1 by 12 BT cube, isn't it? 1 by 12 BT cube is I. And then what is Y? Y is the distance from the neutral axis. So the distance for this rectangular cross section beam from the neutral axis will be T by 2. The thickness is T. The neutral axis will be exactly at half the thickness, T by 2. So if I do 1 by 12 BT cube upon T by 2, I'll get 1 by 6 BT square as the section modulus. So I know the section modulus, and by using the formula bending moment upon section modulus, I'll be getting the stress value. Once I know the stress value, and if I know the modulus of velocity value of this beam material, can find out how much is the strain that can be induced. We are talking about theoretical calculations, right? So I know how to know the bending moment, friends. Bending moment, this is the fixed point, this is the length. I am applying force here. This force into this length will give me bending moment. Applied force, I know I will be putting some weight, I will be having some pan, and I will be applying some weight. So this force, a load into this distance will give me the bending moment. So bending moment, and then Z I can always calculate. I can measure the thickness, I can measure the width, and by using Z is equal to 1 by 6 bt square, I can find out the Z value. So by taking the ratio m by Z, I can find out what is the stress that is induced in this beam theoretically. And if I know the modulus of elasticity value of the beam material, so as we know, stress upon strain is E, so stress upon E will give me strain. So theoretically, corresponding to a given load, how much will be the strain induced, that I know theoretically. Now by using this strain gauge, the same value can be obtained experimentally as such. So this is how I have manually done it. With the help of students, I have prepared so many beams. These were the practical exercises. As you can see, the pan here, I had developed and mounted the strain gauges and for measurement of load. Now this is the commercially available. This is the same beam, as you can see, same cantilever beam. Strain gauges are within, you cannot see them. So I was talking about the commercially available strain gauge load cell, right? So for applying load force, as you can see here, there is a pan, and this is the cantilever beam, as you can see, similar to the beam we just saw. So this is a cantilever beam of rectangular cross section, and I know the length, right? I know the cross sectional details, thickness and width, and I can apply the force or weight, and then I have the strain gauges mounted on this beam, and those are connected to my signal conditioning circuit here. So corresponding to the applied loads, I will be able to measure the micro strain also directly, or this can be used as a load transducer or force transducer. So it can show me the force directly. If I keep the knob like this, it will show me, suppose I applied 1 kg of load. It can show me 1 kg of load. Whatever load I am applying, that will show if it is in the load measurement mode, and if it is in the micro strain measurement mode, it will show me how much is the strain induced within this beam. So this is how what I can do is I can check the calibration of this strain gauge. I have the applied load, and I have the strain indicated by the strain gauge indicator. That is one graph I can have load on x-axis and indicated strain on y-axis. So there I can have two categories, like theoretical strain, which I can calculate, and then experimental strain. So both the plots can be plotted on my graph paper, and the calibration check can be done for micro strain as well as for load. So this is how the strain gauge can be used as a transducer in mechatronics application. Now during the class, we have already discussed how strain gauges are used for various mechatronics applications. If you remember, we had discussed about a gripper, robotic arm or robotic gripper, where I want to measure the applied forces by the gripper. I can mount my strain gauges on those grippers, and what that gripper can do when it is actuated, and if suppose a delicate material, suppose it is holding a bulb, and I should not apply more pressure on the bulb, otherwise it will crack, isn't it? So to control that applied force, we can call it as the tactile force, I can make use of these strain gauges, which will constantly give me the feedback about the applied force, and accordingly the controller will take the corrective action so that only the requisite force is applied through the gripper. So like that, there can be many applications of load gauge, strain gauge transducer. Thank you for watching.